We saw the transconductance curve of the MOSFET is like this, VGS versus ID. Let us try to understand the transconductance curve with respect to other devices, which will give more insight both in terms of the operation of the MOSFET and also how it relates to the other switches. So now let me draw the transconductance curve for the BJT. We have already discussed the BJT curves. So on the x-axis I will put VBE, base to emitter voltage of the BJT, and on the collector, on the y-axis, the collector current IC. We saw the input characteristics or the input curve or the base curve of the BJT, where the y-axis is IB. So the transconductance curve is having the output parameter current IC, and we know that it is related to the base current by beta. So IC is beta times IB. So the curve is like this. We have seen this, where on the positive and VB is positive. So for a very small portion of the base voltage sweep, around 0.5 volts or so, there will not be much collector current, and then further on it after the cut-in voltage of 0.6 or so, you will see the collector current rising proportionally to the base current. And this of course is equal to beta times IB, and when VB goes negative, there is no collector current flow except for thermally generated carriers. Now if we look at the MOSFET, it has something similar. So let us draw the transconductance curve. X-axis, instead of VBE, it will be gate to source. So we indicate gate to source for the x-axis, and for the y-axis it will be the drain current ID. And we have seen that for the MOSFET, enhancement only MOSFET, that's what we use in most of the power electronic systems and circuits. It is like this, where we have here VGS cutoff. Just like you have a cut-in voltage for the VBE, you have a VGS cutoff which is much more sharper, in the sense that below the VGS threshold, recall that we have used this term VGS-TH or VGS threshold. Below VGS threshold, there is no flow of the drain current. There is no inversion layer or inversion channel formed. Above VGS threshold, you see that the drain current follows a square law given by ID is equal to K times, where K is a proportionality constant, VGS minus V threshold whole square. So this is the enhancement MOSFET. Now let us compare this with another MOSFET, family of MOSFET, where again I am going to use VGS as the x-axis and ID as the y-axis, transconductance curve. And let us say we have something like this. You would have seen this type of transconductance curve. This is actually called the depletion and enhancement. So here, the tick mark here indicates VGS off, and here you will have, at when VGS is 0, short circuited, gate source is short circuited, there will be some drain current, IDS, shorted gate source. So IDSs, there is a finite amount of IDSs, and beyond that again you will see the drain current increases. And here again VGS, there is the square law dependency for ID, which is IDSs into 1 minus VGS by VGS of whole square. So this is typically for depletion enhancement MOSFET. We do not use this in power electronic circuits, but this is the depletion MOSFET, the transfer curve, where you will see that when VGS is 0, when the gate voltage is 0, you will see that there is a finite drain current flowing, and that is why this device, depletion enhancement MOSFET, is called a normally on device. And when you keep moving negative for the VGS, at some point here at VGS off, drain current becomes 0, and that is where it reaches its off state. There is another similar device which you would have encountered previously. Again, I am going to use VGS as the x-axis, ID as the y-axis, and you would see a current you would see a transconductance curve like this. This is VGS off, and you have IDSS. So here you will see only depletion region. So why do I say this negative VGS as depletion region? When you give a positive voltage, you see an inversion layer getting formed, which means that the electrons in the channel are getting enhanced. So therefore it is enhancement MOSFET. But when I give negative gate source voltage, the electrons in the channel get reduced, depleted. Therefore it is the depletion region. So the negative VGS gate source voltage region is the depletion region, positive is the enhancement. Here you have only the depletion region. Which is the depletion region? Try to recollect, try to recall. The junction FET or the JFET has a characteristic like this, which is nothing but the depletion only FET, also called as the junction FET. Junction FET doesn't have the insulation between the gate and source like the other MOSFETs. That is why you cannot go positive, because if you go positive, then the P and N will become positive and you will have a short circuit forward biased PN junction. The ID curve law is same as the square law of a depletion enhancement MOSFET type. So this is how you distinguish between the various MOSFETs. So remember that these two devices, depletion enhancement MOSFET and the JFET, are normally on, meaning that when VGS is 0, they are on. They are on devices. They are normally on devices. Only when you make VGS go negative, they gradually start going towards the off condition. At VGS off, they become fully off. BJT and enhancement MOSFET, when VGS is 0 or VB is 0, IC is 0 in the case of the BJT, ID is 0 in the case of the MOSFET. Therefore, these two devices are normally off devices, and this type of devices are the ones that are prevalently used in power electronic circuits. Now, let me introduce one more item here, one more component called the internal body diode, which is very, very specific to the MOSFET. We drew this figure before, a representative visualization of a MOSFET. You have the drain, and this is the source metallization, and you have the source lead, and in between you have this three layers: N-type, P-type and N-type. So for the gate side, you have an insulation and then a metallization where gate is connected. So you have the gate, source and the drain, and a metal oxide insulation insulating the gate metallization to the P substrate. So you have the N-type part, the P-type part, and again the N-type coming in there, and P substrate. This is called the substrate, which is lead is brought out, but it is internally always connected to the source. So this is how normally it is done, so that when you get the packaged MOSFET, you have drain, gate and source. The substrate is normally not brought out. It is internally shorted to the source. Now you see this is source. When a source is positive, what would happen? If source is positive, you have this connected to PN. PN would be a PN junction. So if source is positive, more positive than the drain, then this PN junction can act as a reverse diode. So this direction you could have current flow, because that would act like a PN junction. So this, when you reflect it into the symbol of the MOSFET. This is the gate, and you have the drain, you have the source, and the substrate which is connected to the source. So this is the drain, source, and the gate. This we know. Now from drain to source, to bring in this effect where the substrate is internally connected to the source, and it behaves as a reverse connected PN junction, is the internal body diode. So this is the internal body diode which you get as a bonus in the case of the MOSFET due to the substrate source interconnection. So this internal body diode is actually a bonus, where you will see that this body diode is used for several applications where the inductive current freewheeling happens through this. And if the internal body diode is not there, one will have to put externally a diode across the device, as we do in the BJT. So this is an advantage from the point of view of MOSFET as a power semiconductor switch.